Now, before we get started into similar triangles and specifically focusing on them, we first of all need to establish what makes two shapes, or two figures as we call them, similar. And what are some key properties that we need to know about similar figures? Now, essentially what makes two shapes or two figures similar with each other is one of these figures will be an enlargement of the other. Now, they might not necessarily be in the same rotation, like you could flip it, you could rotate it and it'd be in a different orientation, but one is still in essence an enlargement of the other. And as long as that's true, then we've got similar figures. Now, what's important to note with similar figures is there will be some key properties that will be true with similar figures. The first thing is because they are an enlargement of each other, the actual angles that exist on each corresponding vertice will be the same. And we call that the figures or these shapes will be equiangular. That just means that each one of these corresponding angles will be the same as each other. And the second property that we can actually determine from this is if we look at corresponding side length ratios, we'll notice that they will all be in the same ratio. Now, ratios is when we look at, dividing one side by the other effectively. So if we look at corresponding sides, say, of this larger figure, this AB, which would correspond with this AB over here, the AB dash being the enlargement. If we did this larger one divided by the smaller one, the ratio that was created from that will equal each other's corresponding sides ratio. So this BC divided by BC over here. So you look at that, that would be 2 divided by 1 with the AB. The BC would be 6 divided by 3, both of them equal 2. And you'll find that that is the same with when we're looking at the corresponding sides of CD and DA. Now, essentially this figure that we're actually getting here, when we're doing it in this form, is actually how much of an enlargement this second figure happens to be of this first figure. So it's a scalar factor is something that it can be referred to as. So this is essentially twice, each of these lengths are twice the sides of the original down in here. So with all figures and shapes in general, they are similar if they're an enlargement to each other, and these two properties will be true if that's the case. So the first thing that we need to be able to do with triangles is we need to establish or be able to prove that two triangles are similar. Because if we can prove that two triangles are similar to each other, we can start to find unknown side lengths and things like that. But before we can actually do that, we do have to ensure that we actually have similar triangles. So this is where we actually do a lot of the work from our angle theorems. And similar to when we were doing our angle theorems, we have to justify why certain angles are going to be the same as each other, or justify each step with a reason. So we're going to focus on this figure here. Now, to prove that these two triangles, this triangle ABC and this triangle DEB, are similar, we either need to prove that they have all the same angles, or we need to prove that the corresponding side lengths are all in the same ratio. Now, in this case, we don't actually know any of the side lengths, so we're going to focus on the angles, and we need to prove that they're all the same. So when I'm looking at this, the first one that I actually look at that piques my interest is this angle just here at the vertice of B that's shared from triangle ABC and triangle DEB. In that angle is the same point for both. So the first thing that we can say is the angle at B between A and C is equal to the angle at B between D and E. But every time we do that, we have to give a reason. Now, because they share that angle, we actually call this common. So that's our reason for them two being the same. The next one that I look at is, and you could look at either one of them, but I notice I've got these parallel lines here, and I have this angle here and this angle here that are both the same as each other. Now, if we think of our angle rules here, let's actually just describe them to each other, but we've actually got corresponding angles, and that's our reason for this. So this will be angle at A between B and C is equal to angle at D between B and E. And as I said just before, they are corresponding. Now, we could, with triangles, go and prove that the third angle is also the same as each other. We've got a couple of reasons we could actually use now. They happen to be corresponding again, but at this point, because we know we're dealing with triangles, we can actually stop at this point and go, well, if two of the angles are the same, the third one has to be the same as each other, because otherwise it's not going to add up to 180 degrees. So essentially at this point, we've proven enough to say that they are equiangular. So what we can now say is triangle ABC is similar to, now this is the little symbol to say that it's similar to, triangle DEB. And we generally give a reason as well. Our angle just stands for that they're all equiangular, is our reason for them being similar. So you can see here that because we've been able to prove that all three of those angles have to be the same, we can now say that these are similar triangles, and triangle ABC is an enlargement of triangle DEB. Now, we're just going to quickly show that one more time with these two triangles, SRT and RPQ. So when I'm looking at this one, the first one that I notice is they've given us some information here. They've given us this alpha on both, like, you know, at the vertice T and the vertice Q. So the first thing that I can say here is the angle at T between R and S has to be the same as the angle at Q between P and R. Our reason here is it was information that was given to us. So we actually just write it was given as our justification. The next thing we've got to do is we've got to find another pair of angles that must be the same. This time here, I don't have any parallel line theorems that I can go by, but I do notice that we do have some vertical opposite angles just here, which means that these two have to be the same. So this one's going to be the angle at R, but for triangle STR, that'll be between S and T, is equal to the angle at R again, but this time it'll be between P and Q. And as I established before, these are vertically opposite angles. So now, as before, we don't need to establish that the third one are equal to each other, because for it to be a triangle, it has to add up to 180 degrees. If the other two are equal to each other, it means the third one must be. So we can conclude at this point that triangle RST must be similar to triangle PQR. That'll do. And our reason, once again, is we've proven that they're equally angular. So it's just angle, angle, angle. So essentially with triangles, we can prove it in two ways. I've only shown the equiangular here because I know that's going to be the questions that we're going to be tackling to begin with. But if we did know the side lengths instead, if we could prove that they're all in the same ratio, as long as we can prove that all of them are definitely in the same ratio, then that's still a proof of similar figures and similar triangles.